When we talk about the origin of the universe, most of us picture the Big Bang, a singular titanic event from which all space, time, matter, and energy burst forth. It's the leading theory, the model that has shaped our understanding of the cosmos for nearly a century. From textbooks to pop culture, the Big Bang reigns supreme. But science is not about clinging to sacred cows. It's about constantly testing our ideas, no matter how well loved they are. So today, let's pose a dangerous question. What if the Big Bang never happened? What if the universe did not spring from a singular explosion 13.8 billion years ago? What if everything we think we know about the beginning is just a story we told ourselves? A story that could, someday, be replaced. And what might replace it? In this episode, we'll look at the best reasons we have for believing in the Big Bang, and some of the best reasons to doubt it. We'll dive into competing models, both classic and cutting edge, that offer different visions of how the universe might have come to be, or might always have been. And along the way, we'll wrestle with some of the most fundamental questions science can ask. Did the universe have a beginning at all, or has it always existed? So, grab a drink and a snack, and let's journey back not just to the dawn of time, but beyond it, to a place where beginnings and endings might not even exist. Why do we believe in the Big Bang? For all of its strangeness, the Big Bang isn't just a shot in the dark. It rests on three major pillars of observational evidence, pillars that are, for now, keeping it standing as the dominant cosmological model after replacing the post-Newtonian steady-state model. It has needed tweaking over the years, and still has legitimate criticisms, which we will also discuss today. But let's begin with its strengths. First, we have cosmic redshift. In 1929, Edwin Hubble discovered that distant galaxies are moving away from us, and the further away they are, the faster they are receding. This led to the idea that space itself is expanding, and if you rewind that expansion, you eventually reach a point where everything converges. Expansion implies a denser, hotter past, and by extension, some kind of beginning. And as our telescopes improved, we could not only see things redshifted far away in space and time, but also see their interactions with each other, way back when, and it did confirm they were closer together then too. Second, there's the cosmic microwave background radiation, CMB, a faint glow of radiation that fills the universe, discovered accidentally by Penzias and Wilson in 1965. This afterglow is incredibly uniform, and it's exactly what you'd expect from a universe that was once hot and dense and has since expanded and cooled. It's often called the echo of the Big Bang, a snapshot of the universe when it was just 380,000 years old, practically a baby in cosmic terms. It wasn't microwaves back then either. The universe had a density and temperature more like that of a star's surface, so it was emitting wavelengths more like what we'd actually see with our eyes, and that redshifted over time. It also means it is impossible to look beyond this point, further away in time or space, at least with light. Everything got absorbed too easily. We may one day be able to detect cosmic neutrino emissions. They would have dated back to the first seconds after the Big Bang without being absorbed, but for now, the CMB, also called the surface of last scattering, is a wall beyond which we can only guess. Third, the abundance of light elements. The Big Bang theory predicts that in the first few minutes after the universe began, conditions would have been just right for the formation of certain light elements, mainly hydrogen, helium, and a dash of lithium. Had the density or duration not met a fairly narrow window, we would either have even less helium and deuterium, if things had thinned out faster, or the universe would have a lot more heavier elements and would have possessed them long before star formation, and we can see the general change in elemental proportions over deep time. When we measure the proportions of these elements across the universe, they match those predictions with remarkable accuracy. Taken together, these observations make a compelling case for the Big Bang. It's a model that explains not just one thing, but a suite of interconnected phenomena with a relatively simple framework. And in science, simplicity is often a virtue. Admittedly, the Big Bang is not actually that simple, especially when throwing cosmic inflation, matter to antimatter ratios, and a number of other issues that have popped up. No theory is without its problems, and as we'll see next, the Big Bang has some issues that kept scientists wondering, and in some cases, looking for alternatives. Common criticisms of the Big Bang. For all of its elegance, the Big Bang theory isn't without its rough edges. Over the decades, cosmologists have poked and prodded at it, and while many problems have been patched up, often with clever additions like inflation, some critics argue the theory's need for extra scaffolding suggests something deeper might be wrong. Let's look at some of those more persistent criticisms. The Horizon Problem. When we look at the cosmic microwave background CMB, we find the temperature of the universe is astonishingly uniform, to within 1 part in 100,000, but that's weird when you consider the universe's size and the speed of light. In physics, when two regions reach the same temperature, it's because they had time to exchange energy, like how a cup of coffee left out will eventually reach room temperature by radiating heat to the air. In the early universe, that exchange could only happen at the speed of light. But when we calculate how far light could have traveled in the age of the universe when the CMB was released, about 380,000 years after the Big Bang, it's not nearly far enough to explain how regions on opposite sides of the sky ended up so perfectly synchronized in temperature. They should have been causally disconnected, like two friends who live on opposite sides of the world and have never met. No calls, no letters, no chance to coordinate, yet somehow those regions do have nearly identical temperatures. It's not that we wouldn't expect the early universe to be much the same temperature everywhere, but it shouldn't have been that similar. In general, in physics or math, random initial conditions do show variations. Drop a million pebbles somewhere, and you expect to have some piles and thinner spots, for instance. To smooth out more, in terms of temperature, they have to be able to exchange energy or information. Again, like mixing two fluids of a different temperature, it takes time and interaction for them to level out. But if your expansion is carrying things away from each other too fast for that to happen, then they cannot mix and smooth out to the degrees we see. That's the Horizon Problem or Homogeneity Problem. Distant parts of the universe are too similar to each other given the time they had to communicate or equilibrate according to the speed limit set by physics. This is where we get into inflation, a theorized burst of exponential expansion in the first fraction of a second. It offers a solution by positing that all the regions we see today were once much closer together within causal contact. This is not the normal expansion of the universe after this time unto the present either. Inflation itself is a hypothesis added on to the Big Bang to fix this issue, and not everyone is convinced it's the final word. Amusingly, to me at least, during the inflationary period, nothing was interacting with their neighbors as everything was flying apart from each other faster than light speed. During inflation, the universe's temperature dropped from unimaginably hot to very cold, dominated by vacuum energy. Afterward, everything blasted back up to insanely hot temperatures, and this took place over a few trillionths of a trillionth of a trillionth of a second. We'll examine this more in our upcoming episode looking at epochs of the universe. There are a lot of objections to inflation, and while I love the idea, I tend to share many of those reservations. Unfortunately, this is not the end of our problems, though. The Flatness Problem. Measurements show that the universe is incredibly close to being geometrically flat. But what do we mean by flat in cosmology? In everyday terms, flat means what you'd expect, like a piece of paper or a calm lake. In cosmic terms, flatness refers to the geometry of space on the largest scales, which is determined by the total energy density of the universe. Remember that all energy, not just mass, bends space-time. There are three possibilities. 1. Flat universes. Parallel lines stay parallel forever. The angles of a triangle add up to exactly 180 degrees. Light rays travel in straight lines indefinitely. This happens when the density of the universe is exactly at critical density. If it's even a little off, two beams running side by side should either cross or diverge eventually. 2. Closed universe, one with positive curvature, like the surface of a sphere. Parallel lines eventually meet. Triangles have more than 180 degrees. Such a universe would eventually stop expanding and recollapse. We assume this is not the case these days. Number 3. Open universe or negative curvature. Here, it looks like a saddle. Parallel lines diverge, triangles add up to less than 180 degrees. Expansion would go on forever, growing ever colder and emptier. The Big Bang model allows for all three shapes, flat, open, or closed, depending on the total amount of mass and energy in the universe. If you are trying to picture how a triangle could have more or less than 180 degrees of internal angles, try drawing one on a sphere, like a basketball or a piece of fruit. You'll see that the total internal angles add up to more than 180 degrees. That's positive curvature. You probably do not have a saddle handy. It was more of a mental reference in the past, I imagine, But if you have some Pringles or even a trumpet horn lying around, try drawing a triangle on those. Those internal angles will add up to less than 180 degrees. That's negative curvature. And if you start trying to draw parallel lines on these objects, you will quickly notice how things get strange. This is where non-Euclidean geometry starts to show up. I know non-Euclidean has become a byword for surreal or reality-bending images, think of MC Escher drawings, but most examples in physics and cosmology are pretty tame. They're just referring to the way straight lines drawn on curved surfaces, like a sphere, break Euclid's fifth and last postulate, the parallel postulate. It turns out the parallel postulate only works perfectly on flat surfaces, like paper or chalkboards. Mathematicians have been debating its validity long before modern science arose. Anyway, here's the catch. Flatness is unstable. If the universe starts even slightly open or closed, just a hair above or below the critical density, that small deviation should get amplified over time. A tiny initial curvature would grow, either ballooning into extreme openness or curving into a closed, doomed universe. Yet what we observe today, 13.8 billion years later, is the universe is astonishingly flat, to within 1 part in 100,000 of perfect flatness. This means that at the earliest moments, the universe's energy density must have been balanced on a razor's edge, correct to at least 50 decimal places, or else it would have veered wildly off course long ago. This is one of those examples of eyebrow-raising improbabilities that come up in discussion of a fine-tuned universe or the anthropic principle. See those episodes for more on that. But that's the flatness problem. Why was the early universe so exquisitely balanced? Without inflation or some kind of fine-tuning, there's no obvious reason for it. It's a bit like tossing a pencil in the air and expecting to land perfectly balanced on its tip. Not impossible, but wildly improbable. And again, inflation helps by stretching any initial curvature flat, the same way inflating a balloon smooths out wrinkles. Nonetheless, it's an extra ingredient added on to patch the problem, and not everyone is satisfied with the patches. The Monopole Problem. Grand unified theories, GUTS, predict the existence of magnetic monopoles, hypothetical particles that have only one magnetic pole, either a north or a south, unlike all known magnets which always have both. According to the theory, the early universe should have been littered with them, yet after decades of searching, we haven't found a single magnetic monopole, which is a pity because as we discussed in our Clark-Tech compendium, material made out of magnetic monopoles, mag matter, would be an unbelievably strong material we could build ring wards or classic Dyson spheres out of. Why does the theory say so, incidentally? Normally, if you have a bar magnet with a north and south pole and you cut that in half, you get two new magnets with two new poles, not a north magnet and a south magnet. But back when the universe was too hot, all the forces were unified. And if you ever wondered what that meant, practically speaking, there weren't any quarks or electrons yet, and no other current particles like the ones that transfer forces, like the electromagnetic force, that magnets separate under. Again, we'll talk more about that in the Epochs of the Universe episode, but none of these forces were distinct since particles that emit and or carry them did not exist. And as the universe cooled and they emerged, symmetry breaking occurs, and you have a lot of relics left over that could only have formed in that era but would also remain around nowadays. Magnetic monopoles are one of them. Models in that era were predicting at least one per cubic kilometer, if not a lot more, but none were found. Again, inflation saves the day as it conveniently dilutes monopoles to undetectable levels by expanding the universe so quickly that they become vanishingly rare. But if you're starting to see a pattern here, Big Bang Theory with inflation explains things neatly, but only after you bolt inflation onto it, you are not alone. Dark energy and complexity creep. In its original form, the Big Bang model did not include dark energy. The mysterious force caused the universe's expansion to accelerate, nor did it include dark matter, the invisible glue holding galaxies together. Over time, as new observations came in, these components were added. This process of patching can make a theory seem less elegant. Some critics argue the Big Bang has become bloated, a kind of cosmological Rube Goldberg machine, rather than the simple, elegant, inevitable model it once appeared to be. See our dark energy episode for more details. The Singularity Problem. Finally, and perhaps most troublingly, the Big Bang Theory posits that the universe began from a singularity, a point of infinite density and temperature where the laws of physics break down. Scientists do not like singularities. They are a sign that our current theories are incomplete, that the math has stopped being meaningful. Mind you, all that expansion implies is that the piece of the universe we can see emerged from something far smaller. The original universe could have been a singularity, or a very small object, or even infinite in size. In short, the Big Bang explains a lot, but it also raises deep and difficult questions. Maybe the universe did begin with a bang, or maybe the bang is just a shadow on the cave wall, an illusion cast by deeper realities we have yet to uncover. Steady-state theory. Before the Big Bang became the standard model, the leading alternative was steady-state theory, which had a lot of earlier incarnations even before Newton, but was formally proposed in 1948 by Hermann Bondi, Thomas Gould, and Fred Hoyle, who ironically coined the term Big Bang as a jab at the rival idea. Hoyle has a reputation as a bit of a crank at times. I've always had a soft spot for him, even though he was clearly a bit of a curmudgeon, maybe because I look forward to being one myself one day. I do tend to feel he got robbed of a Nobel Prize for nucleosynthesis, and one of the justifications was for his support of theories deemed rather fringe, one of which is steady-state theory, which I think is wrong but raised some valid points. Steady-state theory argued that the universe has no beginning or end. As it expands, new matter is continuously created to keep density constant, giving the universe a kind of eternal constancy, no singularities, no early hot dense state, no beginning at all. In this case, Hoyle suggests that spontaneous bits of new energy might emerge, and by default take the form of simple hydrogen. Probably because I learned about the theory more or less the same time dark energy came out, when I was still an undergrad, which itself proposes new bits of energy in the form of space-time erupt everywhere regularly. I never saw why this was a super controversial suggestion. Also, I tend to assume there's some higher and eternal and probably infinite layer of reality out there anyway, which is basically a steady-state setup built with finite big bangs or subverses erupting inside it. That is not a particularly rare or controversial notion in physics. The issue is that it tends to just be an assumption without evidence, whereas the Big Bang has a good deal of evidence for it, and steady state, at least for the observable universe around us, has quite a lot against it. Still, for a time it held serious weight, largely because it takes a lot of time to gather evidence as equipment improves. It fits the idea of a universe that looked the same everywhere and at all times, perfect cosmological principle, a comforting idea to many. However, it couldn't account for several observations. The discovery of quasar distribution showed that the universe looks different at different epochs, something a steady-state model cannot explain. Worse still, the cosmic microwave background, a relic heat signature from a hot, dense earlier state, was a death blow. Steady-state couldn't predict or accommodate the CMB. Despite some modern tweaks like quasi-steady-state models, it's largely been abandoned as a viable alternative. I do like to keep up on them, though. I have a personal fascination with even the more fantastic cosmological models, and they are far more out there than we're covering today. Plus, I encourage folks to think way outside the box. When a theory has big holes in it, sometimes it just needs a patch or two, like inflation, but other times it needs an outright replacement, and people can be too wedded to old ideas to look for a new one or to listen when one is presented. We always need to be careful to stay open-minded and objective. Plasma cosmology. Another alternative comes from Hans Alfvén, a Nobel laureate in physics who championed plasma cosmology. In this view, the universe is dominated not by gravity but by plasma, electrically charged gas, with electromagnetic forces playing a major role in shaping large-scale structure. Alfvén envisioned an eternal, evolving cosmos without a singular beginning. Plasma phenomena could, he argued, explain filamentary structures we see in galaxy clusters without resorting to dark matter or Big Bang initial conditions. But plasma cosmology has its problems. While plasmas are abundant, electromagnetic forces cannot fully explain the CMB's uniformity, the large-scale structural formation over billions of years, or the precise abundance of light elements. I first encountered the theory when Eric Lerner wrote his book The Big Bang Never Happened in 1991, and I saw a copy at the library. It was one of the first real physics books I ever read, and I was 10 or so I probably gave the topic more credence than it probably deserved, but we also were lacking a lot of supernova data we get in the late 90s and early 2000s then. It remains an interesting but largely fringe idea today. It has also spawned a lot of variations, some more fringe or controversial than others, like the electric universe hypothesis, others more mainstream. We're exploring some pretty far-out ideas today, and it can be tough to separate cutting-edge hypotheses from outright fringe science. The theories we're talking about might not have much experimental evidence yet, hard to come by when you're tackling the origin of time itself, but that's a far cry from scientists who fake data just to push an agenda. That's exactly what happened in one of the most notorious scandals in research history, often called the Scientific Watergate, now examined in riveting detail by the Nebula original documentary, 17 pages. Meanwhile, over on my latest Nebula exclusive, Mass Drivers on the Moon, we look at how giant electromagnetic catapults could transform the moon into a bustling cosmic shipyard, launching the raw materials we need to build the habitats, power stations, and maybe even megastructures to finally break the grip of scarcity. You can watch Mass Drivers on the Moon, 17 pages, and every episode of this show early and ad-free on Nebula. Get a lifetime membership for just $300, or go annual for $36, a full 40% off. Head to go.nebula.tv/IsaacArthur to join us and start exploring. Conformal Cyclic Cosmology, CCC. More recently, Roger Penrose proposed conformal cyclic cosmology. In this model, the universe doesn't have a start or an end. It moves through infinite aeons. We had devoted a whole episode to this and on ancient ghost universes, so we'll skim it quickly. Each aeon begins with a Big Bang-like event and ends with a cold, empty expansion. But Penrose argues that the physics at the end of one aeon can be mapped via conformal transformation onto the beginning of the next. Again, see that episode to have that translated into plain English. In CCC, the Big Bang isn't the origin of everything, just the latest rebirth. Penrose even claimed to see potential evidence in the CMB, concentric rings that might be signatures of black hole collisions from a previous aeon. However, this remains controversial and not widely accepted by the cosmological community. Again, I love the idea, but generally, if you hear me say I love some cosmological theory or dislike it, there's not much actual connection to its evidence, just that I find it a fascinating idea. And CCC offers a tantalizing way to think about an eternal universe without a true beginning. Emergent universes and Braneworld scenarios. Another approach sidesteps singularity altogether: emergent universe models and Braneworld scenarios. In these ideas, space-time and matter are not fundamental. They emerge from some deeper reality, a pre-existing structure or a quantum gravity regime where familiar concepts like space and time do not yet exist. We also discussed this in depth recently in our look at untangling string theory, so we'll move over it quickly. Braneworld models, particularly those inspired by string theory, propose that our universe is a three-dimensional brane floating in a higher dimensional bulk. Collisions between branes could create Big Bang-like events without requiring a singular start, just a cosmic clash in a higher dimensional arena. These ideas are highly speculative, but they open the door to universes that did not begin with a bang, or at least not the kind of bang we were used to imagining. Quantum graphity and causal set theory. Pushing even deeper, some models suggest that space-time is not fundamental, but emerges from more basic structures. Quantum graphity proposes that space-time is made of nodes and links, like a giant cosmic network. And yes, I said quantum graphity, not quantum gravity. This because it pictures the universe as more like a graph-like structure, again, of nodes and links. Early on, this network is unordered, like a liquid, and as the universe cools, it undergoes a phase transition into the smooth space and time we experience, much like water freezing into ice. Causal set theory takes a different route. It models the universe as a growing set of discrete events, like points in a graph, with causality linking them. No continuous space or time at the bottom, just a web of relationships. In both views, the Big Bang is not the origin of everything, it's just a transition, a phase change, a reorganization of something deeper, but we'll save a deeper dive of them for another time. Eternal inflation. Inflation was originally invented to solve the horizon and flatness problem, but it came with a side effect: eternal inflation. In this model, inflation doesn't end everywhere at once. It keeps going, spawning bubble universes endlessly. Our universe is just one bubble where inflation ended and a Big Bang happened. But globally, there was no single initial Big Bang. Instead, there is an endless multiverse, forever bunning off new universes, each with its own Big Bang event. In this view, the beginning is a local phenomena, not the start of everything. Simulation hypothesis. Finally, there's the wild card, simulation hypothesis. If our universe is a simulation, a creation of some higher intelligence or civilization, not necessarily a godlike being, but potentially even a classic omnipotent creator god, then the Big Bang could simply be the program's initial condition, the cosmic equivalent of booting up a computer, though this does not have to be a computer. It more or less works the same for any created universe whose rules are under the direct control of someone who is not bound by them themselves. In that case, asking what came before the Big Bang might be like asking what was on a hard drive before the simulation launched. It might be irrelevant to our reality or permanently inaccessible. While not a scientific theory in the traditional sense, it's a philosophically intriguing possibility that reminds us we might not know what we don't know. We have quite a few episodes on the topic for those interested. Conclusions. The Big Bang remains the best model we have for the history of our universe, at least our observable universe, but it's not the only idea on the table, and it's not without its problems. From eternal steady states to brain collisions, from cosmic cycles to the possibility of simulation, alternatives invite us to think beyond the singular explosion we usually picture. Whether the Big Bang happened or not, whether it's a beginning or just a local event, the universe remains a mystery far deeper than any single theory can contain. And science, true science, is about following the evidence wherever it leads, even if it overturns our oldest and most cherished ideas. To quote the great Carl Sagan, the cosmos is all that is, or ever was, or ever will be. And considering such immensity, we shouldn't be surprised or dismayed if it takes us a while still to figure out how it works or where it came from.